The X chart is a control chart for the number of non-conformities. In this lesson, we calculate the control limits using the Poisson-Distribution. And hello again to this lesson, which essentially has two learning objectives. At the end, you should be able to calculate the control limits using the Poisson-Distribution. And you should be able to implement this knowledge in a control chart and interpret it. This lesson is divided into two chapters. In the first chapter, we will use the Poisson-Distribution to calculate the control limits. And in the second, we will enter this limit in the control chart and discuss how it is to be interpreted. This picture shows the relationship between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics, shown on the left, can be divided into two different categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. But we don't want to go into detail about them here. Second, there are the attributive characteristics. Those are all characteristics one can only count. On the right side, we have the different control charts for attributive characteristics with a white and yellow background. As you can see, there are 6 control charts for attributive characteristics. As already mentioned, this is about the X chart for the number of non-conformities. Let's start the calculation of the control limits using the Poisson-Distribution. A unit can be one part or a whole end product, or all parts, for example, 200 of a sample. As an example of a unit, we shall use the sample of a die-cast part. Let's assume that this is sufficiently complex to be able to show numerous different defects. 2 defects are shown here as examples. Defect A shows a blowhole on the surface. Defect B shows an incomplete injected tooth. Other defects could be, for example, burrs or other inclusions. The table on the right contains some information from the test planning and the test results. A sample of 200 pieces was taken every day. This was continued for a total of 100 days. The parts were checked and the following total number of defects were found. Failure or defect A was found total of 138 times. The defect B 248 times. Defect C and D a total of 150 and 265 times respectively. Thus, a total of 801 errors were found. This data forms the basis for the further calculations. The first formula on the left is the probability function of the Poisson-Distribution. We will need this to calculate the control limits, where x bar is the average number of defects per unit. xi is the number of defects in a sample. The average number of defects found in a sample results from the quotient of the total number of defects found and the number of random samples. In this example, there are almost 8 defects in one sample. Now we come to the actual calculation of the control limits using the Poisson-Distribution. We do this with MS Excel and the Poisson.dist function. See below on the right. In the first input field, x, we need to enter the number of defects for which we want to calculate the probability of finding exactly this number in a sample. For example, what is the probability that exactly 16 defects are found in a sample? So, if you expect 16 defects, then enter 16 in the first field. The mean field here corresponds to the average number of defects per sample. We had previously calculated this x bar, and it is 8.01. If you set the cumulative field to false, the output is the individual probability. Here, small p(o) with a value of 0.0046, as can be seen in the table. The probability of finding exactly 16 errors in a sample of 200 parts is therefore 0.46%. If you set the cumulative input field to true, the previous individual probabilities are added up. Here, in the large p(o) column, that would be the sum of all individual probabilities from n0 up to and including 16. The result is then 0.9962. It is precisely these summed probabilities that we need to calculate the control limits. Let's create the necessary space for this, and we will continue. So, what do we see in this diagram? On the left of the y-axis are the values for n. As a quick reminder, n is the number of defects per sample. The x-axis is for the probability of finding exactly x defects in a sample. The blue bars show the Poisson-distributed individual probabilities. For the calculation of the control limits, a non-interference probability in the process must be specified beforehand. This is usually 99 or 99.73%, which would be equal to a 6 sigma range. This means that there is a 99% or 99.73% probability that no interference in the process will have to be made during an ongoing series production. Since this lesson is aimed at experts, it is assumed at this point that the terms related to random variation are known. With a 99% probability of non-interference, 1 minus alpha is 0.99 and alpha is 0.1. For the two-sided distribution, alpha half is then 0.005. As we will see shortly, due to the discrete distribution of the values for the cumulative probabilities, large p(o), there will be no values that are exactly 0.005 or 0.995. Therefore, the following conditions apply to defining the limits. The lower control limit, x lower, is the largest x value that satisfies the following condition. The cumulative probability must be equal to or less than alpha half. For the upper control limit, x upper, the cumulative probability must be equal to or greater than 1 minus alpha half. When we draw the limits in a moment, this will become a bit clearer. Back to the lower control limit. Based on the selected non-interference probability, we are looking for the x value for which the following condition is met for the first time. X lower is the largest value of the cumulative probability, capital P(o), which is equal to or smaller than alpha half. So the value that is for the first time equal to or less than 0.005. This is the case when x equals 1. So the lower control limit for the control chart is 1. We now do the same for the upper control limit. Here, we are looking for the value of x that satisfies the following condition for the first time. X upper is the smallest value of the cumulative probability, capital PO, that is equal to or greater than 1 minus alpha half. So, the value that is equal to or greater than 0.995 for the first time. This is the case when x equals 16. The upper control limit for the control chart is therefore 16. Now we come to the creation and interpretation of the X chart. In this control chart, the number of defects per unit is plotted on the y-axis. In our example, the number of defects per sample of 200 pieces. On the x-axis, the number of the sample. In our example, 1 day corresponds to a random sample. The number of defects per sample was entered in the control chart for 100 consecutive days. The previously calculated lower control limit was plotted at 1 and the upper control limit at 16. Due to the selected non-interference probability of 99%, all values can be expected between the control limits with a probability of 99%, or strictly speaking, even with a probability of 99.32%. Only when a value is above or below these limits, it is considered to be a limit violation. In such a case, the cause must be found and the process readjusted if necessary. In our example, the lower limit could also be omitted. After all, fewer mistakes are better than more. On the other hand, a sample with no defects at all would also offer the opportunity to examine how this positive event came about and to use this knowledge to improve the process. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The control limits of the X chart for number of non-conformities are calculated using the Poisson-Distribution. The non-interference probability in the process is 99%, but can also be 99.73%. 99.73% would be equal to the 6 sigma range. 1 or more values above the upper control limit is an indication of an out-of-control process, which may then have to be readjusted. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye!